When a program runs, the memory it uses is generally divided into three parts. First, obviously, we need some place to store the code, the machine instructions that make up the program. The interesting part about the code section is that it is usually treated as read-only, so you should not modify the instructions of the program as the program runs. In the first few decades of computers, though, it wasn't unheard of to have code which is what we call self-modifying. Conceivably, you can come up with some very clever kinds of optimizations. You can use some kind of trick that modifies the code as it runs and thereby achieve some efficiency. That sort of thing in the old days was occasionally justifiable because the systems were seriously underpowered, but also because the programs people wrote were generally relatively small to the sort of stuff we write today. When writing the medium to large-sized programs that we tend to write today, it's hard enough as it is to write the program in the first place and to get it correct. So clever tricks like modifying the code as the program runs are almost always just way too clever for your own good. They just add complexity and confusion to what's already a very complex system. So again, modifying instructions as the program runs is just not something we do today. The data portion of a program, however, obviously needs to be written at runtime. It needs to be written during the course of execution of the program, so it's not kept read-only. And the data of a program is generally split into two sections, one called the call stack and one called the heap. In short, the call stack is where we keep all the local variables of every function we invoke, and the heap is just where we put everything else. We'll talk more about the heap later, but for now let's just look at the stack. When we program in machine code, the usual practice is to organize the code into units called functions. And a function in machine code is really just like what we saw in Pidgin. A function is a unit of code which we can invoke and pass arguments to it, and then the function returns a value when it's done. In Pidgin and other high-level languages, the operation of the function is transparent to us. We really don't have to concern ourselves with what's going on in memory as they execute, but of course in machine code we have to arrange all of that stuff manually. And by far the most common way to do this is to use what's called stack-based execution, where all of the local variables of the functions we invoke go in what's called the call stack. The call stack simply is a contiguous chunk of memory which we have staked out for this purpose, and as our program runs, each time we invoke a function, we store what's called the frame of that function, the collection of all of its local variables and argument values. We add that frame on top of the stack. So say when we execute a program, the stack space is empty, it doesn't contain any frames, but then we invoke our first function, and the frame of that function, let's say here in this case main, the frame for that invocation is placed on the top of the stack, which currently is the very bottom of the stack space. When the function main invokes another function, cat, the frame for that invocation goes on top of the stack, so it goes immediately above the frame of main. When cat then invokes dog, the frame for dog goes on top. When dog invokes fish, it goes on top of dog. And when fish invokes bird, it goes on top. And finally, when bird invokes llama, that again goes on top. So if we pause the program at this point and look at the stack, by virtue of the fact that the frame of llama is at the top of the stack, that tells you that that invocation of llama is the function that is currently executing. The frame at the top always belongs to the currently executing function. Also notice that when the program executes, it needs to keep track of where the top of the stack currently is, because that tells it where to place the next frame when another function gets invoked. Now, when the currently executing function returns, like say llama here returns, the idea is that we no longer need the stack frame, so we simply move the pointer to the top of the stack, we move it down back to the previous frame. And now say here after llama returns and bird starts resuming execution, well, if bird then invokes another function, like say moose, then the stack frame of moose is written over where the frame of llama was. So note that when we get rid of frames, we really don't have to delete them in any sense. We don't have to zero them out. We just move the stack pointer such that later on that section of memory is just going to be overwritten by new frames. Also note that when a function returns, execution is supposed to resume at the point from whence the function was first invoked. And so within a frame, we need to not just store the local variables and the argument values that were passed to that function. We also need to store the return address, the address to which execution needs to jump back when the invocation of that function is over. So that's stack-based execution, and it's precisely what's going on behind the scenes in Pidgin and other languages when we invoke functions. It's just that when we directly code machine instructions, we have to do this all explicitly ourselves. The only thing I've left out here is what about the return value, the value returned by a function invocation? Well, there are various ways to handle that, like say your program might operate under the convention that the return value from a function should be stored in a register, such that when execution, say, jumps back from moose to bird, bird knows where to look to find the return value. It looks in a certain register. That's just one way to do it, and there are other conventions that are just as workable. You're probably somewhat familiar with the Jonathan Swift book Gulliver's Travels, or at least probably you've seen the Disney cartoon version. Well, something in the book which is not covered in the cartoon is that in the land of Lilliput, there's this war going on between the two political factions, one called the Big Indians and one called the Little Indians, and the whole debate is about whether or not when you crack an egg, should you start on the big end and crack that side first, or should you crack the little end first? And the satire, of course, is that people are fighting over something which is really trivial and totally arbitrary. Well, it turns out that CPUs have to make really the same kind of arbitrary choice. And the choice is this: when we copy the bytes from a register to memory, or from a memory to a register, do we copy the big end of the register into the bytes first, or do we copy the little end? For example, if our machine is big endian and say we have a 4-byte register that contains the bytes 0A, 0B, 0C, 0D, when the CPU then executes the instruction copy that register to address A, the 4 bytes of the register are then copied to the 4 bytes starting at address A in this manner, with the most significant byte, the big end 0A, copied to the first byte of the address, the second byte B copied to the next address in memory, and then the third byte copied, and then finally the last byte of the register copied. If our system is little endian, however, and we do the same thing, we copy the content of a 4-byte register contained with the same content to address A, well, we start by copying the little end, the least significant byte of the register 0D, to address A, and then we work from right to left, copying the bytes into the successive bytes of memory. And then finally, for the sake of consistency, if we copy from memory to a register, well, just imagine the arrows in these diagrams reversed, so the arrowhead is on the other side of the line. So say on a big endian system, when you copy from a register to an address in memory, and then copy immediately back from that address back to the same register, well, the register just remains unchanged. So again, the argument is usually made that this is a totally arbitrary decision. It doesn't matter which system you choose, both are perfectly workable. The only real concern is that when you exchange data between a big endian system and a little endian system, you need to be cognizant of this difference. Otherwise, you can end up having, say, a big endian system reading data which it assumes is with the bytes in one direction, when in fact they are the other way around. Now, I actually disagree that this is truly an arbitrary choice. I think it actually really represents a historical mistake. The way things should be is that all systems today should be big endian. However, it's just not the case. The Intel processors, for instance, are little endian machines. My objection to little endianness is that it only makes sense as long as you visualize memory as an array of bytes stacked on top of each other, as arrayed vertically. In these diagrams, the addresses of memory are increasing as you go up, that you could just as well diagram memory with the addresses going in the other direction, increasing downwards. Either way, as long as you're thinking of memory as something arrayed vertically, then little endian and big endian make equal sense. However, when you diagram memory horizontally, it is totally unnatural, at least in the Western world, to diagram the addresses increasing from right to left. We always diagram the bytes of memory increasing from left to right. And so the problem is that if we visualize memory arrayed horizontally, little endian becomes totally backwards. Unfortunately though, just because of historical legacy, this is a problem we're pretty much stuck with.